Hi everyone. So today's lesson is called Products of Radicals. This is section 8-5, by the way, from your textbook. But you'll see I added in here simplifying radicals because I really think that's the more important focus of this section. That's the thing that products of radicals are important for. This also goes back to those complex numbers that some of us struggled with a couple of chapters back. When we were doing like the quadratic formula and we had to do exact values for the square roots. That's going to be this same thing. So this is the stuff that I had said, maybe after we get through this, that quiz would go better for you. Okay, so just kind of keep that in mind. So the whole point of this section is that if you have a square root of a number, or any root, really, it could be a cube root, fourth root, whatever, but I'll stick with square root. Like square root of 20, I can break that up into multiple square roots multiplied together. Okay, so kind of the whole theory behind this section is that this is allowed. And the reason that that's important is if you look, square root of 4, since 4 is a perfect square, I can make a whole number out of that. I can make that a 2, and then I can call this 2 square root of 5. And that is considered to be a simplified version of square root of 20. Okay, so that is an exact value. If you typed in square root of 20 into your calculator, you would get a big, long, crazy decimal. This is considered to be more mathematically precise, and that's why this process is important. Okay, so sort of the process that we talked about this the first time we did these is just knowing your perfect squares. And I'm going to take a quick second and just kind of jot them at the side of the page here. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. So that's where I'm getting these numbers from. Okay, so these are our numbers that are perfect squares. Hope I'm not missing any. And of course I'm going to be missing some because I can't go on forever here, but I say usually up through 12 you're pretty safe. Okay, so let's just do a quick example of one of these. We kind of just did, but example 1, we'll do the square root of, let's see, square root of 200. Okay. And so my goal here is to write this as square root of something times square root of something, and I want one of my two numbers, one of my two values, to come from this list. Because if it can come from this list, then I can take the square root of it. And I really would like it to be the biggest number I can find, because if I can write the biggest number possible here, that'll leave the smallest number possible as my leftover number. Okay, so looking down this list, I know, for example, 4 goes into 200, 25 goes into 200. But again, I kind of want to go as large as I possibly can, and so I'm zoning in here on this 100. So I can write the square root of 200 as the square root of 100 times the square root of 2. Okay, and then square root of 100 is 10, so this would be 10 square root of 2. And this would be my simplified answer for square root of 200. Okay. Now, this process doesn't just work for square roots. It also works for cube roots, fourth roots, fifth roots, and that's what we started learning about yesterday, was all of these other types of roots. So, let's suppose I had the cube root of 875, and I wanted to simplify that. Okay. So I'm going to follow kind of the same process. I want to write this as the cube root of something times the cube root of something. But this time, what I'm looking to simplify is a cube root, not a square root. Okay? And so I don't want perfect squares in here. Now I want perfect cubes. Okay? And your perfect cubes you might not know off the top of your head as well as you know your perfect squares, but let's come up with them real quick. So 1 cubed is 1. 2 cubed is 8, 3 cubed is 27. These obviously get bigger a lot faster. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. 7 cubed, I believe, is 343. 8 cubed is 512. Okay, mental math fails me at 9 cubed. But I think it's 729 actually. And then 10 cubed would be 1,000. Okay, I don't expect that you know all of those off the top of your head. In fact, the only reason I know them is just that I've worked with them so many times, okay? So this might be a little bit trickier for you, okay? But again, you could make the list at the side of your paper. You are allowed to use a calculator for these problems, okay? So you could real quick type in 1 cubed, 2 cubed, 3 cubed, and so on. And I'm looking for, again, the biggest number from this list that would divide evenly into 875. So skimming down this list, I come across 125, and I know 125 is going to divide evenly into 875. So I could say this is the cube root of 125. And then let's see, 875 divided by 125 is going to be 7. By the way, I did cheat and use a calculator on that. Again, I would not expect you to know how to do all of these, off the top of your head. And then I know that I can do the cube root of 125 because it's a perfect cube, because it's on my list. So the cube root of 125 would be 5, and that would be 5 times the cube root of 7. And that's simplified. Okay? So this process works the same no matter what root you're looking at, but I want you to kind of consider, long term how effective this is going to be. For example, if I asked you to simplify a 7th root of 9,641. I have no idea if that simplifies nicely or not, by the way. Just made that up. But 7th roots means that your fancy list down the side of your page would have to be all of your powers of 7. Okay? I know I don't know my powers of 7 past maybe 2. So this method is quick. It's easy if you know your list of numbers, but probably not super effective beyond like cube roots, okay? Because I'm betting that you don't know your powers of 4, your powers of 5, your powers of 6. Even these powers of 3, we're probably stretching it a little bit, okay? So I'm going to show you a second method here to do the same thing, and kind of just like when we did rational exponents, the method I'm about to show you, the downside of it is that it takes longer, okay? It's more writing. But the plus side of it is that it's thorough and it will work for all roots. Okay, so it will work for 5th roots, 12th roots, whatever kind of roots you're looking for, you can use this same method. Okay? So I'm gonna stick with this cube root of 875, but I'm gonna show you a different way you could have come up with this same simplification. Okay? So again, I'm starting with the cube root of 875. And what I'm going to do, just like I did with the rational exponents before, I'm going to make myself a factor tree. Okay, so I have to think of 2 things that multiply to 875. Well, again, I don't have to know that off the top of my head. I really just need to know one thing that divides into 875. Smallest thing I can think of would be 5. So 875 divided by 5 is 175. Okay? And then I'm going to split that 175 by dividing by 5. So I get 5 and 35. And then 35 is 5 and 7. Okay, so there's my factor tree. Now here's how I work with this one. Remember when we did rational exponents, we were looking to see like how many pieces it would split up into? This is a little bit different. If I want cube roots, that means I want 3 numbers that are multiplied together that are exactly the same. Okay, so I want a group of 3, and I have that right here with 5s, right? So this tells me that the fact that I have these 3 5s, that I'm going to be able to put a 5 on the outside of my radical. Okay? Now looking at my factor tree, I don't have 3 of anything else. This is telling me that I must have a group of 3. So there's my group of 3. This 7 is left over, so that's going to go back on the inside of my radical. Okay, so whatever you have the correct grouping of goes on the outside. Whatever is left over goes back on the inside. Okay, that's how this method works. Okay, we could have used that for, what was that very first one we did? Square root of 200. So let me do that one real quick with this method so you can see what that looks like. Square root of 200. Again, if you can look at that and say, oh, well, I know it's 102, you can do the square root of 100, pull that number out. Or you could say, well, this is 2 and 100. 100 is 2 and 50. 50 is 2 and 25. And 25 is 5 and 5. This is a square root, so the number is not written, but we know that it's really a 2 if it's a square root, right? That means we're looking for groups of 2. And again, the reason we're looking for groups of 2 is 2 of the exact same factor means you have a perfect square, right? 2 squared makes 4, and 4 is a perfect square. So I've got 2 2's there, and I have 2 5's down here. So that means on the outside of my radical, I can pull out a 2, and I could pull out a 5. Okay, I don't have any other pairs of anything, so back inside the radical I have this one lonely 2, and that goes on the inside, and then I could multiply these back together and make this 10 square roots of 2. Okay, so that was the same thing we got for that example before. Okay, so that would be using the factor tree method. Again, this takes a little longer, but this is thorough. This will get you to your answer every single time. The other thing I want to point out, one of the common mistakes I see here is people trying to use like these numbers, okay, that are like buried within the factor tree. You're only looking at the prime factors, meaning the ones at the bottom of the tree. Okay, I want to try one with variables real quick, which is a lot less scary than it sounds. Okay, example 4. Sorry, my handwriting's so messy tonight. I know this looks terrifying, but we're going to do the 4th root of 3,888 x to the 6th, y to the 8th. Okay. We're going to treat the numbers differently from the variables, so I kind of divide that up in my head first. I'm going to make a factor tree for that 3,888. And again, I know it sounds daunting, but probably less daunting than knowing all of your perfect powers of 4 and figuring out what goes into 3,888. So this is 2 and cheating again, 1944. Oh, duh, I should have known that one. This would be 2 and 972. That would be 2 and 486. This would be 2 and 243. Now my 2's won't work anymore, so now I'm going to go with 3's. This would be 3 and 81, 3 and 27, 3 and 9, oh, and 3 and 3. Really squeezing that in there. Okay, give you a minute to catch up on that factor tree. Okay, so because this is asking for a 4th root, that means I need powers of 4, meaning I need 4 of the same factor multiplied together. So I see a 2, a 2, a 2, and a 2. So I have 4 2's. There's a group of 4 2's. That means I get to put 1 2 on the outside of my radical. So for every grouping, I put one of that number on the outside. Okay, because what I'm really doing here is the 4th root of 2 to the 4th power, and those kind of cancel each other out, and I'm left with just the 2. Okay, now for the 3's, I have 1, 2, 3, 4 3's, so let's see, that's these right here. So I know I can put a 3 on the outside. But then I do have a lonely 3 down here. I have this 3 here that got left out of the grouping. Okay, so that 3 is going to go back up inside the radical. Okay, I sometimes use the analogy of like a prison break here, which I realize is not the best analogy to use for this kind of thing. But like this 4th root here is the guard. Okay, and you can't sneak past the guard unless you're in groups of 4. So here we've got a group of 4. They're going to make it out. Here we've got a group of 4, they're going to make it out, and this one lonely 3 does not quite make it out, so he gets to stay in jail. Okay? Juvenile, I know, but it's functional. Okay, so now let's talk about how to deal with these variables. And this part you probably will not have to write out every single time, but I would write it out this first time so you understand where it came from. So I have x to the 6th. If I wrote out a factor tree for x to the 6th, it would look like this. Right? It would be 6 x's all multiplied together. And just like I did over here, what I'm really looking for is groups of 4. So I have 4 right here, and that means I get to put 1 x on the outside. Now over here, I didn't have enough to make another group of 4, so that means I have these 2 x's get to stay on the inside. Okay, they're leftovers. Okay, so the only thing that gets to come out are the groups, and the groups are determined by this number out here. Now let's look at my y's. So for y to the 8th, that would be y times y times y times y, 8 times. Okay, so now when I look at groups of 4, I have a group of 4 here, so I get to bring one y outside. And I have a group of 4 here, so I get to bring another y outside. And I don't have any leftovers, so none of my y's stay inside the radical. Okay? So when I clean all of this up and write it as a final answer, I'm going to multiply all of this stuff back together and all of this back together. So on the outside here, I guess I'm going to put my final answer down here at the bottom, would be 6xy squared. And then you would have a 4th root of, that 4th root, by the way, just came from the fact that we started with a 4th root. Whatever you have when you begin is what you're going to have at the end. And then you would have a 3x squared left over on the inside. Okay? So those variables, you're making those groupings just like you did before. Okay? So again, it's up to you whether you want to do the quick method of just saying to yourself, what perfect powers of 4 go into this number. My guess, let's see, this here, the 4 2's would have made a 16. Whoops. And then the 4 3's would have made a 81, so 243. My guess is that you would not have looked at this number and known that 16 and 243 were perfect factors without doing some of the division that you would have needed for the factor tree anyway. So that's why I like this method. But again, it does take a little longer, so if you are able to take that shortcut like we did before, I highly encourage you to do it. The other thing is, when you've got these variables, you probably don't need to write out 6 x's to realize that you could make one group of 4 and you would have 2 left over. Okay, so again, I wrote this out just to kind of illustrate what I was talking about, but with the variables, you shouldn't really have to do that every single time. Okay? There was one thing I kind of glazed over at the beginning of this lesson, because I thought it was pretty easy, but I guess I should talk about it. We'll just call this example 4. Is kind of going the other way. So what we were doing just a minute ago is we were taking radicals and breaking them into pieces that were multiplied together. We can go the other way with that. We can multiply radicals together. So if I had the 5th root of 4x multiplied by the 5th root of 3x squared, I can multiply these together by just multiplying the things that are inside the radical. However, I'm only allowed to multiply radicals together if this number, the index, is the same in both of them. Okay, and I don't do anything with that index. That just stays a 5th root. So my answer here would be this is a 5th root of 12x squared. No, sorry, 12x to the 3rd, because I have an x here and an x squared here. Okay, 5th root of 12x cubed. Now technically with my answer, I should simplify if I can, which is that process we just went through. But looking at this one, for example, I know there's no groups of 5 factors in 12. Okay, there's no power of 5 that goes into 12 besides maybe 1. And 1 doesn't really do you any good. And I also can't make a group of 5 out of this x cubed, so there's nothing I can really pull out here, so that's just my final answer. But if I did come across something where I could pull something out, I should. If you encounter, and I mentioned this, but just to kind of point it out, something like this, the cube root of 4x times the 5th root of 3x squared, these two cannot be combined, okay? So cannot be multiplied because their index is not the same. Okay, so you can only multiply if the index, meaning that number out here, is exactly the same. Okay, they're not like terms, so you can't combine them. Okay. Okay, I think that really does it for this lesson, at least for lesson 8.5. Just want to check over your homework real quick and make sure there's nothing else that we're really missing. Oh, there is one type of problem on your homework that I want to make sure I talk about. We've actually already talked about it, but the wording can be weird. So I'm going to throw one more example at you, and then I promise I'm done for today. Okay, so let's say I give you something like this. So this says the square root of 250 equals the square root of a times the square root of 10, and that equals b times the square root of 10. What they're really doing here is stepping you through that process that we did with the very first example, where we were able to just look at a number like this one and figure out what are the two factors where one of them is a perfect square and I can pull it out. Okay, and that's what it's telling you to do. Is it saying what number is my perfect square factor? And it's even helping you because it's saying it's going to be something times 10. So really all you have to do is divide this by 10. And then when you have that perfect square factor, what does that turn into when you actually do the perfect square? So for this one in particular, 250 is equal to 25 times 10. So this would be square root of 25 times square root of 10. Okay? And then that square root of 25 would just become a 5. So this would be 5 square root of 10. So what this question is really asking you to say is that A is equal to 25 and B is equal to 5. Okay, so I thought it was just kind of a weird wording of that question, but that's really what they want you to do. And there's, I think, a couple of them in your homework like that. So just wanted you to see that ahead of time. Other than that, I think you are set to go. You are just doing lesson 8.5 today out of the textbook. I don't remember the exact problem numbers, but if you turn around and look at the back board, they're all listed up there for you. Tomorrow you will go over this homework assignment and do some review over today's lesson and yesterday's lesson, and then I will be back next week to teach you one last new lesson in this chapter. Okay? Good luck. Feel free to text or email if you do have any questions or concerns.